The frame and the suspension are a high-risk element. The frame has to be rigid, and that's why we use thicker aluminium profiles, increasing the safety factor. The independent suspension system allows the Rover to drive through rough terrain at high speeds. What can be said about the commonly used rocker bogie suspension? We designed a new manipulator mechanism which allows for the same torque as a mechanical actuator while reducing the weight of the Rover. Our drill is an innovative prototype based on oil drilling devices. We created two types of unique wheels. The first one is stiff and durable, which is an advantage on wet terrain. The second one is soft and suitable for a rocky site. Thanks to the elastic spokes, we were able to reduce the weight. The most unique electronic system in the Rover is a radio modem which has a very large signal range. The heart of the Rover is built using STM32 microcontrollers. The main module uses a Discovery development board inserted into a PCB board which we have designed. This is a powerful 32-bit F4 microcontroller. All of the data is transferred by this board to the other modules. The same unit is used on an independent manipulator board. There are several absolute encoders made by us and mounted on the manipulator, which increase the movement precision and improve the inverse kinematic system. The Rover is steered with a joystick and the robotic arm is controlled with the gamepad. The remote control and autonomous mode are both controlled with our own application written by our IT subteam. For the autonomous task, we are using an NVIDIA Jetson TX2. Although this is not the most up-to-date generation of Jetson's development board, it is still powerful enough for our needs. We are using our own unique decision engine for the pathfinding algorithm. We are using a 2D scanner mounted at the very front of the Rover for obstacle detection and avoidance. It can detect obstacles within a 5-meter radius. Our team is split into sub-teams and works in the same way as a regular company. We use management tools such as Trello, Cloud, or Gantt chart. Thanks to these tools, we are able to systematically check our progress. The system which we have been using helps us in meeting our goals and deadlines. Legendary Rover 7 easily handles driving up slopes, can lift heavy objects, and carry out precise tasks like using a screwdriver. Our experience has been used to optimize the Rover and complete the URC tasks. Our tennis ball recognition algorithm is based on a TensorFlow neural network. The second part of the image recognition task will be the invention and development of a more accurate and stable algorithm which detects the marker with a higher probability. We have tested the properties of metals, composites and plastics. Proper materials have been applied to the different parts of the driving system. We have designed two different wheels. The first wheel is rigid and has a rubber tire. After a terrain test, we changed the design to a more elastic one. The most crucial part of the second wheel are the elastic spokes. The wheels retain their initial shape despite a large number of work cycles. We have improved the design of our gripper, which allows us to perform very precise tasks. We're conducting extensive tests for the autonomous systems. We have a pre-tested navigation system and are currently working on debugging and improving obstacle detection and avoidance algorithms. The obstacle detection module is also capable of stopping the Rover in emergency cases, for example, when the obstacles are too close. As you can see, two lamps are mounted at the rear of the Rover. They are dynamically signalizing the autonomous system state. The initial soil examination will be performed on board by the Rover's integral instruments. The onboard test includes physiochemical analysis of soil by checking its temperature, acidity or basicity, salinity, conductivity and humidity.